one mixed node, but are mixed nodes. Okay, 3, 5, 10, something like that. So how does she do it? The traditional way is that Alice just picks separate x's and produces separate alphas, one for each node. Okay? And this is the way that most previous mixed formats have worked, and is why their headers are so big. Because these group elements G, they're, for example, 256 bytes if you're using the mod n construction, and 256 bytes times 5 or 10 is already a kilobyte or 2 kilobytes. Okay? Just the alpha parts are taking up everything. So, can we get rid of that? Well, one thing you can do is there's no reason that Alice has to use a different alpha with each node, is there? She can just use the same alpha, but derive different shared secret keys, because she'll be taking the alpha, she'll be taking yn for the first node to the power of x to get her first secret key, yn for the second node to the power of x to get her second secret key, and so on. So all the secret keys will be different, but the alpha can stay the same. Why doesn't that work? Well, consider again. Remember, the whole point of this is to prevent an attacker from being able to link the incoming messages to the outgoing messages. Okay? So if she uses the same alpha to communicate to the first node and the second node and the third node, then that alpha will appear on the incoming message. So the incoming messages will have one value of alpha from this person, a different value of alpha from this person, a different value of alpha from this person. Then the outgoing messages will have the same alphas but in a different order. And then it's just easy to match up, oh, there's that alpha and there it is there. So this incoming message was this outgoing message. Okay? So we can't do that. It has to be the case that the values of alpha that go out of the mix have to be completely different from the values of alpha going into the mix. It has to be the case that you can't figure out which incoming matched which outgoing. So how do we accomplish this? And the way we do this is by a technique called blinding. So in blinding, each node blinds the value of alpha as it processes the message. And by blinds is a cryptographic technical term. It basically means randomizes, but in a determined way. Okay? So randomized but determined seems contradictory, but it actually has a very strict meaning. So basically it means that Alice and the node can both predict what the output alpha will be given the input alpha, but no one else can predict that. To everyone else it looks random. Okay? So the way this works is that the node n changes alpha by raising it to the power of a hash of alpha and the shared secret s. So note that only Alice and the node know this shared secret s by the security properties of Diffie-Hellman. So those two entities can both compute what this hash of alpha and s will be, but to everyone else it's the hash of something which includes a random component that they don't know, and then we invoke the mystical random oracle model and say a hash of something you don't know is just a random number. Okay? And so anyone else, you're raising alpha to the power of a random number, and since we're in a prime order group, raising something to the power of a random number makes a uniformly random group element. Okay? So to anyone else, it is really indistinguishable from random. Okay? So now let's just look briefly at how Sphinx processes a mixed message. So the first thing you have to do is check that alpha is actually in your group. Okay? So that's here. Let me use the pointer. So that's here. So for some groups, this involves a public key operation. So if you're doing things mod a 2048-bit number, you have to take an exponentiation to check whether you're actually in the group. For other groups like elliptic curves, you don't need to do much work at all. In fact, for curve 25519, you just basically have to check that alpha isn't all zeros. Any other string is fine. Okay? You don't have to check anything really for beta, gamma, and delta because those are allowed to be any bit strings of an appropriate length. So you just have to check that their lengths are fine. So I didn't even write that down. The next step is to compute the shared secret. So you have alpha, you being the mix, have your own secret key xn here, and you take alpha to the power of xn to get your shared secret s. Okay, your shared secret s is then used in this MAC. Remember, there's a cryptographic hash, and the cryptographic part is that it uses this secret s to check that this gamma is really a MAC of beta. Okay? And if it is, that means no one has messed with the header. Okay, we'll talk about how to handle the payload in just a bit. Assuming no one's messed with the header, you can then process it. So now you have to decrypt the header, but you have to do it in such a way that the size of the header coming in matches the size of the header going out. And this is a little tricky because decryption necessarily removes some information. Right? Necessarily, we're going to have some information in there like the size of the node, like the next MAC and stuff like that. And that necessarily removes some information. So how is it we're going to get this header to be the same size after as it is now? And the way, back to the picture here, is that we take the beta and we stick some extra zeros at the end. And with the parameters I was talking about, you stick 32 bytes of zeros, basically double the security parameter. And then you decrypt it, and you decrypt it with your favorite stream cipher. Okay, in our implementation, we used AES encounter mode. That's a lot of people's favorite stream cipher nowadays. Could use RC4. That was people's favorite stream cipher several years ago. Whatever you like. As I said, we use AES encounter mode, which is just you take your message and you XOR it with the encryption stream, and you get some result. Then you chop off the first bit, and that's the node. N prime is the address of the next node to send it to. If there were any other mixing parameters, that's where you would stick them. The next bit is gamma prime, that's the next MAC, and then the last bit is beta prime. Okay? So we extract those values. The next thing is you blind alpha here, like I said before, to get alpha prime. And then you have to get delta prime. The way you do that is you take S as your secret key, and you decrypt the payload using S to get the next payload. And the way you decrypt it is by using what we call a large block cipher. So this is a block cipher like AES, but AES has a block size of 16 bytes. Okay? Bigger than older block ciphers like DES, but we're going to say we want a block cipher whose block size is the entire size of the message. And then we just do one block operation to do the decryption. Okay, and there are a number of constructions for such things. We use one called YNS by Anderson and BM in our implementation. So now we have all the primes, alpha prime, beta prime, gamma prime, delta prime, and we send that on to N prime. Okay? I'll just finish up the last couple minutes by talking about the proof of security. So in Crypto 05, Kamenish and Lisinskaya had a paper which gave 4 properties of an onion routing system that when taken together prove the system is secure, okay, in a particular model called the Universal Composability Framework. And what this proves is that the cryptographic format itself doesn't leak information. Now, you can still leak information if the mixing strategy is bad, but that's the fault of the mixing strategy. So we just say, mixing strategy is what it is. We're just not going to leak any additional information just from the mix format. Okay? Here are the properties. Correctness, this is obvious. The protocol has to work if there's no one attacking it. Okay? Your users would complain if it didn't. Integrity, this is a technical condition. It basically says there's an upper bound to the number of honest mix nodes that'll process a message. So the adversary can't construct a message that will go forever in a loop through your system. It will have to come out eventually. Okay? And this has to be true even if the adversary knows all the private keys in the system. Okay? So it's a somewhat strong condition. Then is wrap resistance, which is even stronger. This is even if an adversary can choose a node's private key, it can't construct a mix message that that node will process to produce a specific desired mix message. Okay? Again, another technical condition. Security is the important one. Security here is the usual indistinguishability game. So you have two messages with paths that go through an honest node.